much. Good morning. Yeah, this morning, we'll talk about integration of sensor networks, or maybe more general of Internet of Things, of the Internet of Things into IT infrastructures, which so far yesterday, when if you remember, we heard a lot about how to create sensor networks and sensor network testbeds and so on. And the question certainly remains, I mean, what do we do with these sensor networks? Are they just there? Or how do we process the information that we get from sensor networks? And one important topic certainly is how do we get the information into the IT infrastructures where people are really usually working with, PCs and mainframes and servers of all kinds and so on. So how do we bridge this gap? Certainly you could say, well, there's always some kind of gateway, and we collect the data in the gateway and then make it available to the IT infrastructures. But the question is, can we do this more seamlessly? And this is what this talk is more or less about. So briefly, a few words concerning myself. So I'm, as you've heard from the University of Lübeck, as Daniel is. I've been a full professor of computer science there since 2004. Before that, I did my PhD in Mannheim. Alexei, we talked about Mannheim yesterday. We found out we have a lot of common relations from Mannheim. Then I was a postdoc in Montreal, in Canada, for 1 year. Came back to Germany, became an assistant professor in one of the first private German universities, which actually doesn't exist anymore. The business model was probably not very good. And then, just in time, I left the university and went to Braunschweig University, which is also more or less in the north. In research, I'm very much interested in more or less two huge fields. One is networks, all kinds of modern network structures like sensor networks, ad hoc networks, and things like that. And on the other hand, I'm very much interested already since at least 20 years or so in software to organize distributed systems, like middleware and things like this. And since a few years, myself and mostly one PhD student, we have been very much working in the field of service-oriented architectures applied to sensor networks. And this is basically what I'll present today here, the work of the last 3, 4, 5 years of one PhD student who already 1.5 years ago got his PhD in this area. And we are certainly also interested in all kinds of applications, and especially because Lübeck is a very much medically oriented university. We work very much in the field of, or at least more and more tend to work in the field of medical applications of sensor networks of the Internet of Things. So far, probably you haven't seen where Lübeck is. Where is it? So this is mostly Germany, and this is Germany and France and so on. You can easily find, and just in case you have not been able to find it, here it is. So this is Lübeck here, just at the Baltic Sea coast. Very nice place. You'll see a few pictures at least one picture on one of the next few slides, especially of the port of Lübeck, which is very well known. I think it's the biggest port in the Baltic Sea area. Lots of ships arriving there, and this is actually also one of the business cases that I'll show here for why it makes a lot of sense to integrate sensor networks and IT infrastructures. Okay, as I've already said, the talk is mostly based on a PhD thesis of the one written by Niels Klombitzer at the end of 2011. And a number of publications that came from this PhD thesis, which we wrote together. So what are the goals of this talk? What would I expect you to know or understand afterwards? First, I will try to show you that it makes a lot of sense to use so-called service-oriented architectures with the Internet of Things. So service-oriented architecture as one of the main modern approaches to construct business software. And I'll also give a brief introduction into the whole idea of service-oriented architectures. So we want to combine the service-oriented architecture and Internet of Things. SOA is more or less just a concept, and in order to to create applications built on the SOA paradigm, we need some kind of implementation technology. And the most well-known and, as most people say, the best suited technology is web services, and it's certainly something that everybody knows here in the room. So I'll just give a two-slide introduction into web services, and just to give us a common understanding for the remaining things to come in this talk. So we want to have web services as an implementation technology in the Internet of Things, and I'll also show you why this is. I mean, from the idea, it's very straightforward, but from the realization, it's very difficult. Mostly due to the enormous resource constraints that you've already seen yesterday. You know, these tiny little devices with just little memory and very small bandwidth and so on. This makes it very difficult to have web services as a solution on such devices. We'll show how, why this is the case, and certainly we then present solutions. So understand how web services can be realized, and then even more, understand how business process management can be realized in the Internet of Things. Web service is just one thing, so you provide some kind of service accessible on a tiny device, but creating a whole business process. I mean, for instance, graphically describing the business process and then automatically generating software from it and still running this on IoT devices. This is even a step further, and I'll also talk about this a little. So, these are the goals, and here's the overview of the talk. We'll start with the motivation, a logistics scenario, and its business applications. When I wrote the slide, I didn't have the idea that Dick would be in the room here, so hopefully you don't have to correct me too much. So I'm not a business guy, but I'm trying to give my understanding of the business applications. But maybe there's some room of discussions for afterwards or during the talk. Then we'll have a brief look at basic technologies, and well, I'll mostly skip the wireless sensor network stuff, or at least make it very short. Maybe talk a little bit more about service-oriented architectures, and then in the solutions part, challenges/solutions part, we'll mainly cover two things. First, how to implement web services in a wireless sensor network, and then part business process management in wireless sensor networks. So this is the first business slide. Actually, Niels came up with that. Niels actually studied information systems, which we would call in German Wirtschaftsinformatik. So it's a combination of computer science and business management. So he leaned a lot towards business ideas, and that's also the reason why he did the PhD in this field here. So the most important question he started with was, well, you have the strategy of a certain company, the business strategy of the company, and you have information systems. And usually, if you have a business strategy, and companies are usually run by business people, so they said, well, we have this certain strategy here, and now we have to get the right information systems for this purpose. So information systems which support our strategy best. In the 60s, that was very simple, and every IT manager knew exactly what to do: buy an IBM mainframe or rent one or whatever. You could never make a mistake with that. You would never get fired if you buy IBM hardware and software. And certainly today this has changed a lot. There's a lot more competition, and there's a lot more possibilities to configure, to run, to choose your information systems. On the other hand, and so if we talk about the status of this is to some extent, I mean, that's standard. So the business strategy usually uses to tailor the information systems to the extent they are needed. Now the other way around, information systems which enable business strategy, especially new information systems, there's still something to do. I mean, you know, new information systems coming up, like sensor networks, like Internet of Things, and I always remember, I already hear Rob. Is he still already here? Rob, I already hear Rob saying, where's the business case, right? So the question is, how can for a company it can be very interesting, very important. How can information systems, new kinds of information systems like sensor networks or more general like the Internet of Things, how can they influence the business strategy? How can they enable new business strategies? And in his thesis, Niels wanted to show to some extent how new information systems can be integrated into IT infrastructures, into existing IT infrastructures of a company, and how they then influence the business strategy and make it possible to have new business strategies, more efficient strategies, for instance. Business process. So I've talked a lot about this already. What is a business process? Here's the definition of Wikipedia found on this Sunday 2 days ago. So a business process or business method is a collection of related structured activities or tasks that produce a specific service or product for a particular customer or customers. So it's some kind of activity that produces a certain result within a company. It often can be visualized with a flowchart as a sequence of activities, and we'll come to that a little later when we talk about business process management. Here comes the interesting part for the computer scientists already. So if there's a graphical representation, then usually you immediately, at least for me, as I said, I've been working with middleware and so on since more than 20 years. Whenever I hear the word graphical representation of something, then I immediately think about code generation. So whenever you have some kind of formal representation, you'll most certainly be able to generate code automatically and make software production much easier, and this is what we are looking for here. So a flowchart as a sequence of activities. Business processes can be themselves subdivided into further business processes, and they can certainly also be themselves part of other business processes. And as far as I know from my own studies in business, just many years ago, I think modern companies are mostly organized along their processes. So if a company defines a strategy, then the strategy is resolved into the main business processes that are used to achieve the goals of the strategy. I see Dick always nodding, so that seems to be fine still. So this is just to give you an example, a business process. Sometimes actually, I have to say, from time to time I have some German graphics, which I don't have the sources of, but usually they are very easy to understand. So this is an example of a loan application. So someone wants to get a credit from a credit company. So the process starts with the guy coming in, and the first thing that you have to do is, in Germany at least, to find out whether the rating of the customer is good enough to get a loan. If yes, then it continues, and the loan company starts to ask two banks in parallel. So this bank here and this bank here. So invokes the service here. This is a parallel thing here, and then both branches wait until they receive the offer. In the end, select the best offer, and then the process ends. So that's a typical way of how business processes are described. Already, I mean, this is already very much IT oriented. There are lots of things like, invoke. So something is invoked, something is received. That looks like a communication process, which can be easily created. And by the way, this and this here and this also, these are also processes. So the bank, for instance, will also run a process to compute an offer for the customer. Maybe just a final word concerning the business process management, the layers of business process management, in order to give us a better idea of the notions that are used here. So on the if we look at the company and look at the strategic layer, then certainly we have this the business strategy, the strategic development of what the company wants to achieve and how it wants to achieve that. Then we have second layer, something we could call the domain layer, which is mostly related to process management. So here processes are described, but very much in a domain language, not in computer experts' language, but in the language that the domain expert is using. Next step would be to translate this, if we want to, and this is what we want to, if we want to translate this into an IT system in the end, we need to make this more operational, need to make this become something which computer scientists could work with. And this is on the operational layer, usually a workflow. And workflow management systems is certainly probably something that you've heard from time to time in your classes or wherever. So a workflow management system is more or less a system that is already able to implement business processes, but there has to be translation between the domain language, let's say the business language, and the computer science language on the workflow layer. And in the end, certainly this has to, this will influence very much the applications which are based on top of the workflow management system. So sometimes I'm using the word process, business process, sometimes I'm using the word workflow. Usually when I talk about these notions, I use them very much interchangeably, but I guess you understand typically what I mean by this. So here's the image which I promised. It's the port of Lübeck in Travemünde. Here's the Baltic Sea. This is the river Trave, and here's the most important port of Lübeck. And you see, actually, there's a lot of space for very huge ships. And well, due to this port, there's in Lübeck and in the surroundings of Lübeck, there is a number of companies which are very much interested and whose business is logistics of all kinds. Logistics could be, for instance, running trucks, or maybe only running the how it's called, just the machine that pulls the trucks. So often this is actually separate. So there's I don't know the English word. So the machine that pulls the truck, and then the trailer themselves. And these are usually provided by different companies. So there are companies which run these machines. There are companies which run and rent trailers, and then there are certainly companies which operate these ships here. And then there's certainly the company which in Lübeck, in the case of Lübeck, is 50% owned by the city of Lübeck and 50% by a private investor. They run this port here, and they all together organize the shipment process. So unfortunately the next part here is a bit hard to read. At least I think it's hard to read due to the colors. And again, since I didn't have the sources, I was not able to change the colors. But what you can more or less see here is there's a truck on the street. So there's a driving truck, which to some extent has hopefully often access to, let's say, to GSM connections, and via GSM has contact to enterprise IT software. Then in the port, the truck may be parking somewhere. Again, has contact to some kind of enterprise IT, and then finally on the ship, again the truck might to some extent be connected to the enterprise IT. Why is this interesting? What could be interesting information that during these processes here could become relevant for the transport process? Well, first thing here, the truck, at least in experiments that we did, is already equipped with all kinds of sensors, maybe even with the sensor net. What could you be able to find out with such sensors? One interesting thing could be, for instance, did the truck take the route that the driver was told to take, or did he take any deviations for whatever reason? You never know. I mean, logistics is a business where really a lot of criminal things happen, and owners of whatever you ship and whatever is used for shipping in logistics processes are very careful. So they are very interested in, for instance, did the car take any deviations, or was the back door of the truck opened during the transport process? Or is the CO squared concentration changing within the truck? For instance, because there's illegal transport of people within the truck, things like that. All this could be found out and can be very that can be very interesting within the enterprises. Then here on the parking side, so here this is the whole parking side for for trucks. For instance, could it be very important to know what kind of truck parks in which position, and especially what the truck is loaded? It might, for instance, happen that there are two trucks which have both loaded dangerous goods, and if these dangerous goods are too close to each other and something bad happens, like I don't know whatever, some of the barons is losing something of the dangerous goods, and the other one also, and then these are mixed together, then maybe something bad happens. So it could be, for instance, interesting to electronically, automatically know what these trucks have loaded, and then make sure at this point here where the trucks enter the port area, to make sure that trucks which have loaded this stuff here, this dangerous good, and trucks which have loaded other dangerous goods, that they are parked in very different areas of the whole port. For instance, same on the ship. On the ship, for instance, could be very interesting to find out whether the temperature of a transport box remains always below a certain threshold. So usually when you drive your truck here on the street, it's interesting and important, but usually here it's not that difficult, because when the truck is driving, there's lots of energy available for cooling. But on the ship, the truck is not driving, and you have to rely on the energy that the ship is providing. And what often happens is that this energy fails. It fails to work. It's not available, and then possibly the cooling engines won't work anymore. And it would be certainly very interesting to know this very much in advance, especially know this earlier before something bad happens to the load that you have. Yeah? So all kinds of these things, and not only do we have sensors in the truck and on the ships and so on, but we could also have sensors in the parking areas, and in the end maybe we have a complete sensor network here. And what we want to achieve, as I've already said, we want to get the information that sensors provide here on trucks, on ships, on the parking area, at the gate, wherever. Want to make this immediately available in the enterprise IT of a company, because usually people don't access sensors directly, but they access the information which is then available within the IT system. Okay, very briefly, I mean, you've heard a lot about this already, and most of you are wireless sensor network experts, but maybe as a brief introduction, especially for DIG, wireless sensor networks, how do they work? What is their main purpose? Well, we have lots of these little tiny devices here, sensors. You've seen them yesterday. They are equipped with some kind of sensors and some kind of communication device, a processor, let's say an embedded system in general, and some kind of energy supply. That's our usual model of such a tiny sensor node. So what do? They connect to each other, they build a sensor network in order to process information together. And a typical application could be finding out about movement through a certain area. So there's maybe this car is driving through the area of the network, and then there's a number of sensors which realize that something has happened, that a movement event has taken place. And this information could then be communicated to a gateway, and in the end lead to some kind of aggregated information being available in the enterprise IT system. So here, for instance, the information could be where there have been 3 sensors which have registered the movement, and And there's also been a special order. It was first this one, and then this one. And, well, you all know that only this simple application here already has a lot of implications concerning for instance, the time synchronization that we need in such systems. I mean, in order to be able to say something about the order in which events have occurred within the distributed system, we need some kind of synchronized clocks in order to create timestamps which show us the order of events and things like that. All kinds of difficult things. So if we talk about sensor networks, we usually say, well, we have many sensor devices with sensors equipped with sensors and radio. They collect data, and they do this usually in a self-organized way. Sensor network platforms, you've seen some. This is one that Daniel already mentioned. It's an older version of the iSense platform. I won't go into details. You've seen a lot about this yesterday. Now, how do we bring this together with the Internet of Things? To some extent, I mean, there's many people who more or less use, again, wireless sensor networks, Internet of Things to some extent interchangeably. Let's just try to find a common notion for us here together. So, Internet of Things, I think it's more or less clear. It's a digital representation of real things in the Internet, and the Internet IoT technology allows to represent the state of real environments and make it available via sensors, usually in real time, like temperature, light, CO2 movement, humidity, and so on. And then, so this is getting information, and then on the other hand, the second part is also influencing the real environment via actuators. So it's using these possible to influence the real world through actions, and I mean, influencing here doesn't have to be something dramatic. It can be simple things like a switch, a light switch like this one here, or traffic lights, displays, and so on. So this are typical Internet of Things. That's how Internet of Things typically look like. And if we bring this together with wireless sensor networks, well, then we have first the embedded system. I mean, this is more or less the same information that we have with the sensor node itself, sensor network itself. So we have an embedded system combined with sensors and/or actuators with the radio interface, and this is what we usually call a wireless sensor node. If we have many of these, then we talk of a wireless sensor network, especially if they are connected to each other. And if then finally the wireless sensor network is connected to the internet, like here, then we would call this the Internet of Things. And then there are lots of possibilities to how to organize the access to the information. And you all know there's a full load of European projects which deals with how to organize the Internet of Things and how to handle all this the processes here and the structures and so on. So no need to talk about this any further. Most of you are somehow involved in these projects, and probably you know much better details of certain research questions than I do. IoT applications to finish this, well, smart cities certainly one of the most important, especially on the European research agenda. One of the most important things, like typical applications that we've already heard about SmartSantander yesterday, for instance, like intelligent public transport, also in Belgrade, smart parking, SmartSantander, intelligent traffic lights, intelligent street lamps, all kinds of different things that happen in the city. And then there's all these smart X applications like smart home, smart healthcare, smart grid, even smart government. I mean, this is really a challenge. So all this, again, I guess here a lot of the people in the room here are working on one or the other of these applications. So now the question is, how do we actually develop today such IoT applications? And usually, I mean, Daniel, when he stood here yesterday, he did his advertisement of his breakout group. he said, well, there will be a lot of low-level programming. Yes, exactly. That's mostly what is done in sensor network programming still today. So usage of low-level programming languages like C++ templates and so on. What does it mean? Well, it certainly means there's usually long development times. It's very likely that you create bugs in your application. It's usually a high degree of complexity, and most importantly, usually the applications cannot be developed by domain experts. If you keep in mind the business process management on the second layer, we have the domain experts. They know what the processes are in their applications, in their company. And usually what happens if you implement an IT system, then the domain experts, they describe their processes in their language, and then they talk to the IT experts and try to explain what they want, and the IT experts try to understand what they want, and usually there might be some difference in the outcome. So actually it would be much more helpful if domain experts could be integrated in the development process by already formally describing what they really want, and then the IT expert just use this formal model and translate it further into the applications. Well, then certainly if we just develop monolithic wireless sensor network applications, then they are very poorly portable. There's no reuse, and integration into IT infrastructures usually is very hard. And then in the end, if you even use proprietary communication protocols, then this, especially protocols that you're just using within your own organization, then for instance something like inter-organizational integration will become very hard. So integrate a sensor network of one organization into the IT system of another one, that will be very difficult because they simply don't talk the same language. Certainly it's also incompatible with existing standards in enterprise IT, and service-oriented architecture / web services are such a standard that usually doesn't work with each other, and often you need application-specific heavyweight data. So what could be a solution to this? What we want is a programming, or let's say an application development technology, which allows domain experts to more or less describe the application in a formal way, and then more or less automatically generate the code for the application, and this, most importantly, in a seamless way. Seamless between the enterprise ID part of the system and the sensor network part of the system. So no more barrier between these two, but we want to integrate the two worlds. And the question is, how can we do this? And the answer from our point of view is, well, let's use service-oriented architectures and try to make it possible to run service-oriented architecture technologies on tiny devices. And this is, as I've said in the beginning, that's really a challenge due to the resource constraints. I'll come to that a little later. Just a brief introduction to service-oriented architectures. I guess most of you have heard about that already, but I mean, it's still, since at least 10 years or so, an important and still, more or less hot topic in the IT industry. I mean, it's not that hot as cloud computing, but still, to some extent, belongs to this kind of technology. When it was created, it was actually not one of the few IT technologies which was not the idea of IT experts, but it's an idea of the business people, of the domain experts. They came up with this idea. So what they wanted to have actually is something like a flexible business process management. Usually companies have a pool of business processes which are usually built of some kind of services. So you have a business process like the one we've seen, the banking, and the business process usually consists of a number of calls to existing services. So for instance, give me the Schufa rating, the rating if the customer could get a loan or not. Or ask this bank for a certain service, or ask the other bank for a certain service. All these are service calls. And in general, you can express a business process more or less by calls to services and by some kind of flow language, which for instance lets you describe decisions or parallel executions and so on. This is what a business process usually is. So companies when they are process oriented, when they are organized in a process oriented way, then they have a pool of business processes and they are built from services. And now what happens if a new process is created, a new business process? Let's say, for instance, the company has bought another company and now needs to integrate this, and this leads to creating a number of new processes. What does this mean? Well, in principle, the nicest thing would be if you can create new processes flexibly from existing services available in the pool in an ad hoc manner. Before the idea of SOA, this simply wasn't possible. I mean, there's software available like enterprise resource planning systems, like from companies like SAP or Oracle and so on, and they simply didn't have this. They didn't have a pool of services and business processes that you can flexibly describe. They simply had their software, their applications, and these were more or less very monolithic and couldn't be dissolved into their parts and then used by themselves. So the new idea is pool of services. Whenever there's a new process to be created, just describe it in a possibly graphical way, at least in a way that domain experts can do. Put this description into the configuration software of your enterprise resource planning software, and then everything will be generated automatically. Why do they want this? Very easy. They don't want to. Very simple. They don't want to pay the people from SAP anymore for their job of configuring the SAP software, which is the most important cost factor in running such an IT system. It's not buying the software or renting it. It's paying the people who do the adjustments. And if you can do that yourself as a domain expert, then it will become much cheaper actually. Yeah? So making IT systems more cost efficient for your company.
If it becomes more cost efficient to configure it, then companies will start selling it at a higher price or not?
Well,
it's part of their business model.
Probably that's a question that Dick could answer much better. But I guess so. If a company does this and they really realize this cost advantage, then they have a competitive advantage, at least for a while, which could mean that they offer their products at a lower price and probably can get a better market share. I mean, that's what I would expect from that. Or they simply don't tell and take the additional money as profit. And this works as long as there's no competition. So if other companies do the same, then this will become smaller and smaller. That's at least my naive understanding of how such processes in the business world work. But anyway, to some extent, bad news for us here, right? So are we needed anymore after SOAs have been realized? Well, good question. This is another one of these German language slides. You don't have to understand the stuff here. It just gives you an impression how business software is organized or was organized in the time before service-oriented architecture. So we have these monolithic blocks here, all applications, like a finance application, customer relationship application, supply management application, and they all were monolithically standing next to each other, with the result that most of them had functionalities implemented double or 3 times in each of them. Data had to be copied between different databases with all the typical effects like redundancy and errors which are made, errors in updates and things like that. So lots of problems with that. And the idea of SOA is more or less, well, let's not use the applications anymore. Let's just use services. These are certain blocks of services. And the system itself concentrates around or focuses on processes. That's what we That's what we want to achieve here. Every user has a graphical user interface with which he or she is able to access the process, to run the process, and each of the processes accesses services which are made available by certain systems. And by this, certainly it's possible to avoid redundancies between data storage and also functional services and so on. So in principle, a good idea also not only for making it possible for domain experts to create software, but also to organize your IT structures in a more efficient way. Technically speaking, how do service-oriented architectures work? Well, we have this. Some kind of application software, some kind of application function, and in all service-oriented architecture approaches, especially in web services, what you do is you equip your application code, your application function with a service interface, like the gray one here. And the important thing about the service interface is that it's standardized. So the way of describing it is standardized, and the way of how it communicates with this so-called service or messaging backbone is also standardized. So as a result, every component here in this picture here can potentially communicate with any other component using standard communication technologies. As soon as you publish this service description, and you also say how the service description should be used, it will be possible for other services like this one, for instance, to call this service and get information from it. And what is behind the service doesn't matter. In the service-oriented architecture, it's only important how the interface looks like, what the syntax and the semantics of the interface is, and of the service that is offered. But how the service is implemented is completely unimportant. Yeah? So that can be, and you see, there's lots of possible technologies here, and any good service-oriented architecture approach will allow more or less every backbone technology to be integrated here. Web services, as I said, the most important technology for realizing service-oriented, the concept, the paradigm of service-oriented architectures. That's a specific technology. I guess again here most of you have heard of that or have used that to some or the other way. Yesterday we've heard something about SOAP web services, REST web services. We are talking about SOAP web services here, a more complex technology. And if we use web service for service-oriented architectures, going back here, then we need some kind of way to describe the service interface. And in the SOAP web service world, there's a language available which is called WSDL. Web Service Description Language. It's an interface description language, and what you can do there is describe data types that you want to exchange and messages and ports and so on. So more or less some kind of, to put it very simple, some kind of remote procedure call description. But more flexible. You can do more things, but you can especially describe remote procedure calls, and when being honest, mostly when you think about services in such a service-oriented world, you often think about a remote procedure call. So there's some service offered, and you call this service and you get a result back, and it's essentially a remote procedure call. Doesn't have to be like this. WSDL is much more flexible in this respect, but just for your imagination, that's more or less what it is. So define data types and operations, and then at runtime, the communication partners, so the service provider and the service user, they communicate using so-called SOAP messages. We don't have to understand really the SOAP protocol. More or less, it just says, well, it's a more or less complex protocol, but actually rather how to say. Rather bulky or whatever. It takes a lot of code to express certain information. Yeah? It's XML, And you all know that in order to code something in XML, you need to write a lot, which is in enterprise IT not a problem. I mean, there's lots of bandwidth available usually, and you have lots of computing facilities within an enterprise IT server, and you have lots of storage space and so on. So XML in this world is not a problem. Unfortunately, on a sensor node it is. Doing XML computations, or let's say like parsing an XML document, or even storing an XML message on such a node quickly becomes a problem. And we'll see this again a little later. Just to give you an example how this looks like, so this is a WSDL description of a service which provides a temperature. What the service more or less does is it offers, let's say, a remote procedure that you can call by sending so the operation is called get temperature. You can send a get temperature request to the service, and as a result get a get temperature response back. Here is a description how these operations look like. So the first message here is a batched message without any parameters. You just send the get temperature request to the service provider, and as a result get a message back with one parameter called temperature, and it's of type temperature, and the type temperature is described here as in XML schema. So it's an integer restricted to values between 0 and 50. So this is the description of the service. What happens during runtime? So if a service user wants to call the get temperature service at the provider, then the service user has to send a SOAP message to this provider, which looks like this. And this is the structure of the SOAP protocol. It contains the body of the message, and the body just contains the get temperature message without any parameters. There's lots of namespace thing and so on within XML. But you see 250 bytes. How big is a packet that you are allowed to send via typical sensor network communication technology? Like half, exactly. More or less exactly half, right? So we already have a problem here. This is a very simple message. I mean, it's a bit could have been enough, right? If there's only one service available on this node, and we use 250 bytes, that's a problem. The result is even longer, 346 bytes. Get temperature response, and here's the result also coded in ASCII. So that's one major problem. Messages are much too long, and data that is described and to be stored on nodes has the very same problem. Still, I mean, this we can come to that on the next slide. Using web service has a lot of advantages, and still we think it's a good idea to try to do that. Use web service also in the sensor network world. This is a general description of the web service, especially of SOAP web service technology. What we've seen so far is these two things here, or let's say these three things here. We have seen that how web services are described in this language here. Then we have the SOAP protocol, which is coded in XML. There's a few other things that need to be considered also. One thing that we'll see a bit later is here on top, the business process orchestration. So using up to here more or less, we are able to describe one web service, and all the rest is add-ons. And the top add-on here is how to combine several web services into a whole business process. Yeah? Up here, only one web service. With this technology here, you can do everything you like in order to create one web service, call the web service, use the results, but then the stuff up here, especially this one here, helps you to make it really a service-oriented architecture with business process management and everything. There's some quality of service like reliable transfer and security and so on. This part here is quite important, UDDI and web service discovery, that's service discovery. Typically in a web service world, you don't, when you start your application or when you start coding your application, you don't know all the services that are available. You need some kind of directory services, and this here that gives you access to directories in this web service world. But we'll skip this. This is for us here not too important. But this here, the rest here is also quite important. The transport. So in this part here, we've been able to describe how messages look like, and we've seen on the slide before how a SOAP message looks like. The question still remains: how do we transport the SOAP message from the service user, the one who calls the service, to the service provider? And there's a number, as you see, lots of options. You can even use raw TCP/IP, UDP IP, but you could also use more advanced, let's say, application-oriented transport protocols like HTTP. The advantage is that, for instance, with HTTP, you already get the semantics of a typical remote procedure call for free. You put a SOAP message in you put the get temperature message here into a HTTP request, send it to an HTTP server which is running on the service provider. Then the SOAP message is extracted, the service is executed, and the result, the SOAP response here, is coded back into the HTTP reply or response, and it's sent back in the same interaction between service user and service provider on the HTTP level. So, in other words, if you use something like this, like HTTP or SMTP, you don't have to worry about the transport because HTTP servers are ubiquitous. You can get an HTTP and HTTP clients more or less for free on every device, even on a, let's say, on a Raspberry Pi or on maybe even on a sensor node already. So usually something you don't have to worry about. The only thing is maybe they also produce a lot of overhead, and we'll see that also that this actually is the case. So why using web services? Well, certainly there's a large tool support available for the development process. Web services are simply, since the year 2000 or so, the main implementation technology for all kinds of remote procedure calls in the SOA environment. And companies like Microsoft and Oracle and Sun and IBM and so on, they have all produced lots of technical solutions for supporting the development process of web services. There's also already a lot of technologies available, especially in this field here and in this to really create service-oriented architectures, not only call a single web service. So lots of tools available for this. Heterogeneous platform support is very simple, based on HTTP, XML, SOAP, and so on. You can really cover more or less any technology that you like, and it's also widely spread in enterprise IT environments. So what we, as I've already said, want to do, we want to extend today's SOA technologies to sensor networks rather than developing new solutions. So 1 hour for the motivation. So the next 3 hours we will talk about the solutions. So what do we have? What do we want? Just to summarize this, well, we have wireless sensor networks, IoT. We have SOA, and we have web services. This is all what we've talked so far. And now we want to use these technologies to create an integrated wireless sensor network, enterprise IT or backbone based on service-oriented architectures, which should also be doable for domain experts. So what we need to do is we need to solve the problems that we've seen, especially the resource constraints, and we also want to offer something which is more nicely usable for domain experts, like graphical tools, for instance, which help you in the development process. Okay, so the challenge, just to show this again, well, we have our Internet of Things here, and the original thing that the internet was made for, just getting web pages, is now something we extend by using business processes in the internet. So we have a number of services, we have an application, and the application usually, so it starts a business process and then triggers a number of actions on the different services, and in the end, a certain result will come up here in the application. And what we want to do now is we want to extend this to the sensor network. And more practically speaking, things that we have to realize is well, having our sensor network, again from the logistics process here, enterprise IT, and the user interface to the enterprise IT. First thing that we have to solve is make web services run on these platforms. I mean, here in this area here, this is standard. We don't have to do anything here, but here we have to do something. Sensor network. On top of that, we want to create service-oriented architectures, and if I say this is all means, well, we want to have a fully fledged business process management available in this on this, and also some kind of graphical process modeling. So I speed up a little, but I thought it would be good to see the different facets of the problem and understand what really needs to be done. So web services in wireless sensor networks, how would a possible solution look like? Well, if we go through the technology stack and start here with TCP/IP, UDP/IP, then the use of IP as a transport protocol as the protocol for communicating between hosts has always been difficult in sensor networks, again due to the huge number of IP packets and the overhead which is within IP and so on. So there's a number of solutions which have been looked at, and the most important and current favorite solution is 6LoWPAN, which most of you probably have also heard of. This is nothing which we are going to talk about here in this talk. This is not our layer, so we assume that there's something like 6LoWPAN available. We are much more interested in the next layers coming up here. So the issues that we are interested in is which transport binding to use. In the SOA world, you always talk about transport bindings. What is meant is which transport protocol are we using here. So which transport binding to use, and how to cope with the large overhead on the message layer, especially here on SOAP and XML. So huge messages, can we somehow handle this? And just to give you an idea of how the overhead of web transport service bindings looks like, and this doesn't contain any SOAP messages. It's just the overhead of the transport binding. So here in HTTP you already have. I mean, we did this with a certain application, but you see there's a lot of, in HTTP already more than 500 bytes overhead. FTP the same, and if you use SMTP, so sending your service calls via email to a service user, then you really have really large overheads, and so on. So obviously there's a problem here that has to be solved. So if the main problems that we have to use when we want to use web service in wireless sensor networks is that we don't have a lean transport binding. There was none available. Maybe with the exception of UDP, which basically is not really a transport protocol, at least doesn't provide any service. And this one, which is also a simple protocol which has been developed years ago at our institute. So, no lean transport binding. Then SOAP messages, XML SOAP messages are bulky, and even simple services like the temperature thing, they overburden the available memory and especially the bandwidth of typical sensor nodes. And then finally, if you use traditional tools for code generation, then usually the code is quite large in terms of code size, and it often depends on also large libraries, XML parsers and so on, which also make things quite difficult. So, how does our approach look like in this area? Well, we have made two things. We have invented, whatever, a new transport protocol, which is called So here it just says wireless sensor network transport binding, and the final name then was LTP, lead transport protocol. We'll talk about this a little more. And we have a compression serialization algorithm implemented, and I'll briefly talk about this just on one slide and this on a few more slides. So efficient low overhead XML compression and a lean transport binding. What's the trick with XML compression in the web service world? I mean, you can, if you just do the naive approach, then you can compress any XML document as you can compress any other document. Just use Huffman coding or whatever, and you achieve good compression rates. There's, for instance, gzip as a compression algorithm, also part of the web services standard. So you can use this very easily. But what you don't do in this case is you don't use all the information that you have. And in the web service world, there's an important information that you have, and that can be very nicely used, and that's the structure description. You know how XML documents look like because you have the service description in WSDL. So you know how your descriptions, how the messages will look like if you send a service call to a service user or get the response back. You already know how the structure looks like, how it has to look like. And then you can save a lot of information by just more or less comparing the document that you send to the structure and more or less just code the differences between the structure and the actual document. And this is much less information. So in the end, you can achieve really enormous improvements in terms of percentage of message length. Yeah? So this is one. This is more or less the solution for the long XML messages. Do compression, but not just brute force compression using some kind of Huffman code, but do intelligent compression using structure descriptions. We did this with a general code generation framework. Those of you who've been here last year might have heard about this already, and I just mentioned it here when Dennis talked about this. This is a part of Dennis Pfister's PhD work, the implementation of the Fabric code generator. So it allows to produce very efficient code, which again produces very efficient binary encodings for messages, like average savings compared to XML codings 97%, and the size of the code of the code generated here is just a few kilobytes, 1.5 kilobytes on a typical sensor network platform, which usually is quite okay. So on modern platforms, there's quite some memory available meanwhile, and having this little overhead here is usually okay. So that's the solution for long XML messages. The next question is the transport protocol. So what we want to have, a protocol which allows for seamless integration between wireless sensor networks and enterprise IT service. So a protocol which should be available on every platform. So it should be usable in the internet and on wireless sensor networks, and it should make efficient use of resources. And the protocol that we came up with, lean transport protocol, it has a consistent URL addressing scheme. So it starts with, as you would have expected, it uses the URL scheme for addressing. It has the LTP identifier, and then it's possible to identify especially sensor nodes in a sensor network. We'll see a bit more on this on the next slide, and then a certain service. It uses Fabric for the serialization. It has a certain header compression scheme. I won't go into details here, but it allows to save again a lot on header compression, and it supports arbitrary transport protocols below that. So just to make sure what we do here, that you understand that we exchange something like HTTP or SMTP by LTP. But we still need the layer 4 transport protocol like TCP or UDP. And we have a lightweight gateway which connects the wireless sensor network to the IP-based network. So our adjusted web service stack then looks like this. We have on the message layer, we have an additional compression scheme which we call SMC, and we have on the transport layer the additional LTP protocol. And these two together here, we call this the LTP plus SMC binding, which can be used instead of HTTP, for instance. Yes.
A question. If you would define the main differences or advantages of LTP compared to CoAP, what would it be?
Yeah. Okay. That's an interesting question. Let's not start this discussion because CoAP has, let's say, during the last 2 years evolved a lot, and I think we came a little later. So what I just show here at the moment are results from until 2011. So it doesn't include any CoAP. But yeah, certainly good point. LTP and CoAP are to some extent comparable, certainly. So what kind of communication is possible in LTP? Well, basically everything. So you can just talk outside any sensor network stuff between application server and the application. You can talk using mobile phones, implementing LTP in mobile phones, and you can certainly talk through gateways with different sensor networks. And here, if this is organizational boundaries, certainly it's also possible to talk from an application server through the organizational boundary with other sensor networks. Our architecture that we always have in mind is that there's still a gateway available. So here's the wireless sensor network, and there's a gateway, and for accessing the sensor network, you always use the gateway. So this is how the addressing scheme looks like. So we have this identifier LTP, then we have this identifier for let's say the host or the sensor network. This is let's say the traditional URL HTTP syntax, but in front of that you can additionally identify a sensor node in the network. You have a port number which is used on the gateway in order to identify the correct communication port to the sensor network, and the web service on the sensor which you in the end want to call. So the whole communication process in LTP then looks like this. You have the service consumer, wireless sensor network gateway, and the service provider. And what happens? So if someone wants to talk wants to call a certain web service and wants to get a certain answer back, then you can even use the WS addressing scheme, which allows you to give different recipients for your messages. So here you say, please send a message to this address here. Send the answer to this address here, and this is my message ID, and this is the body. So what happens with this message? Well, it will be packed into a SOAP message, will be transported to the wireless sensor network gateway. Here it will be unpackaged and will then be transferred to the correct sensor node, and this is the message ID to make it possible to identify the answer in the end. So that's of this node here. That's the message ID, and reply to is 0 is the address of this here in the sensor network, and 1 is again the message ID. Okay, then we use the WSN transport protocol, like ZigBee and related things. Here everything is, the service is executed, and then the result is computed, sent back to the sensor network gateway with the correct message number, and here the message is again translated more or less a message being transported using UDP TCP with this address here. That's the reply to address, which has been stored on the gateway until the answer here came back.
So do you assume that the Centar network is a static one?
Sorry?
Do you assume that the Centar network is a static one? Or do you also take mobility of nodes into consideration?
Well, at least the addresses are static. The addresses of the sensor nodes have to be static. But, I mean, this is, there could be multiple hops in between here, if this is the question.
No.
Yeah.
If the node moves from one gateway to another, would you still be able to access it in the meantime?
Okay. Good question. Let's say to that extent it's static for the moment. I'm sorry, I can't answer give you the correct answer. Maybe yes, but I don't know. Okay, so this is not just a theoretical study. We implemented this especially in some business process execution runtimes, especially in Apache ODE and in Windows Workflow Foundation, and used this for a number of experiments, and came up with, for instance, certain results for runtimes for a web service invocation, which is like here for LTP on a PC compared to the same in access to HTTP on a PC, much better because it's a much thinner protocol certainly. And even on this PaceMate platform that you've seen yesterday, it's also still quite good in terms of round trip times. And in terms of packet sizes, the same, right? So here, different terms of different levels of compression. If you compress everything, then you get very small messages compared to the typical SOAP addressing in plain XML with huge message sizes over 500 bytes, and then here down to 15 with everything compressed, header compression, and everything used, which is much better, but certainly also needs some more computing power. Okay, I think I'll just talk about, I have two more things that I would talk about. I just skipped the last one and just take, it's not too important, but the next one I would like to talk about. So we've done this, we've done web services. We also to some extent have service-oriented architectures already done. What we still need is some kind of graphical process modeling. So the question is, how could this be done? And you've already seen this notion of BPEL, business process execution language, which is a language which can be very nicely used to describe business processes in a graphical way. Actually, the standard of BPEL is not a graphical representation; it's a written XML-based description, but it's very easy to derive a graphical representation from that. And we'll have a brief look at that. So, if you look at business process management in the WSN context, there are two things that we could think of. The first thing is something we already have now. I mean, it's integration of sensor networks into business processes which are executed in enterprise servers. So we have services, web services available on sensor nodes, and these services can be called from enterprise IT servers. So there's an application running somewhere on the enterprise IT hardware. And at some point, someone wants to know something which is provided by a sensor node, and then the service consumer could simply do a web service call to this service. So that's the first step, done. Yeah? This works. Second thing is, could it be actually interesting to execute parts of business processes on sensor nodes? So not only offer let's say a passive service call whenever a service call is coming in, then the sensor node does something and then sends the answer back. But could it make sense to even run parts of a business process or a whole business process on a sensor node? I mean, why? Why should we do that? Yeah. So this is something we already have had. If you look back at our application scenario, at the logistics scenario, one could think of the following situation, for instance. We could create a business process where the temperature measurements in a certain transport box, like this one here, and their sending are not pulled by the enterprise IT, so there's not the enterprise IT asking for the temperature every time, but they are controlled by the sensor itself. So the sensor runs part of a business process like this. So it measures the temperature in the box at some certain point in time, and then, for instance, could based on the measurements do whatever is necessary. For instance, start an alarm, or just continue measuring, or go to sleep, or whatever. So far, we don't have this. We just have the possibility to describe a web service which runs on the node, but not the business process. So if something here in this system happens, so when something which needs to be recorded or needs to be communicated, then the result should be sent to the enterprise IDs. This is something we would like to have. And well, the first choice would certainly be, can't we somehow extend the idea of business process execution language to sensor nodes? And this is how a business process looks like in Beeple. It looks, I mean, if you look more deeply into it, it looks very much like the picture we had right at the beginning, the banking example. You know? So the banking example was very simple. This is a more complex process, but in essence, it's absolutely the same thing that you can do here. You can describe flows, you can describe communication with other services like neighbor, whatever. And the question would be, can we use this stuff also on sensor nodes? So this is already standard in enterprise IT systems. Beeple execution languages is something that people know how to use this, but and how to program it and so on. But doing this on sensor networks is still a difficulty. Interpretation, for instance, of Beeple processes. So having a Beeple processing engine which loads the process description and then interprets the process description, which is often done in enterprise IT, is more or less impossible due to resource constraints. I mean, even the process description usually is already too big. So the only solution probably is compiled code, which in terms of footprint is as efficient as possible. Then Beeple is a very powerful language with possibilities of expressing parallelism and choices and whatever you can think of in flow description languages. Everything is possible, and here we come to one first thing. For instance, on many sensor network platforms, parallelism is even impossible. You can't express this in the OS concepts of many of the platforms. So mapping of the possible parallel execution of things in the Beeple process is very difficult. So what Niels did in his thesis, he developed a process partitioning, which allows for cutting the Beeple process in parts and then executing each part of that as a single process, and still keeping the semantics of the overall process. So in principle, you could find a solution for that, but still, we also thought of a different solution for resource-constrained devices, and the solution that we came up with is a state machine-based system. So not flow-based descriptions as in Beeple, but state-based descriptions as in usual protocol descriptions. The system, which we call it SM4 RCD, it's a very much restricted language as compared to Beeple, so not too many complicated constructions, but generation of efficient code is possible. And the interesting thing is that we don't want to have a either or between Beeple or an SM4 RCD. We want to have a coexistence of both, and we even want to make it possible to run both together use both together in one description of a business process. So this is how it looks like, and this is what most of you have certainly somehow somewhere seen. So we have states in the descriptions, and you have events that lead to state changes. So if the system is in a sleep state and a certain timeout happens, then it goes to the measure state, and then certain things again happen. Yeah, that's the typical state-based description. So the question is, how can we combine these two now? I mean, we've talked about this before, and now we are on this level here, and we have now Beeple, and we have this SM4 RCD. How could we combine these two things? This is a typical example of what we've done, again in the logistics process. This is a part of the business process which runs on a sensor node, described in this SM4 RCD, so in a very lean, state-oriented way. So we have the sleep and the measurement state and an alarm state. And then we have the possibility to communicate with other processes, like this one, which is the Beeple measurement process, which is running somewhere on an enterprise IT server, maybe even very far away from the sensor node. And the same here, there's an alarm service which also runs somewhere else. So what happens in the system here is, well, we have this, usually the system here is in a sleep mode. From time to time, on a timer event, it goes into the measurement mode, measures something, and usually then sends this measurement to the Beeple measurement service. The service itself, it just interprets the result it got, and if the temperature is too high, then it triggers an alarm. And triggering an alarm means, in this simple example here, send the message back to the service, and if there's the alarm trigger event happens here, then the sensor node it goes into the alarm state and gets in touch with the Beeple alarm service, which then does the more, let's say, the things that the sensor node typically does not. For instance, it calls the port authority. Maybe even, this could even be a Beeple service. There's a part of the Beeple standard which is called Beeple for people, which even allows you to involve people in processes. For instance, this could be a telephone call to the port authority, automatically issued by the system, which a sensor node typically wouldn't do, but the enterprise IT system could easily do. So you see, integration of people and this the state-based system works very nicely, and the state-based description is very lean and very simple. It can be very easily converted into very efficient code. For instance, we have done some measurements and implementation both on a GENIC platform and a pacemate platform. So all in all, these are the code sizes here in bytes for the whole thing. So SM4 RCD model and the RTP framework and the web service, all for something like 50 kilobytes, which typically is doable on such platforms. Okay, so message size is also using SMC much better than XML, but on the other hand, what you always have to keep in mind certainly that there's much more processing necessary. Okay, I think we can make a tick here, and I would stop the presentation here. I have a few more, a final problem, but it's not too important, so I'll skip this and just come to the end, to the summary. We've seen that integrating embedded systems into existing enterprise IT system would allow for new services, like keep in mind the transport, the logistics problem, and it would also allow for seamless IoT integration into this. SOA and web service technology is certainly a clear plus as integration platform, and we've shown or Niels especially has shown in his thesis that it's actually really doable on resource-constrained devices, mostly due to the modularity of the web service concept. And actually, all the solutions that we have that we've described here are completely conform to the web service standards. So they are not any special solutions; they adhere to the standards. Yeah. So we've presented a number of solutions to allow for SOA-based integration, like we have this lean transport protocol binding, we have this graphical modeling language, and we have something which I've not talked about anymore due to time restrictions. Some literature, and again, also I'm going to put up the slides here for you to be available. And apart from that, I'm done, and Thank you for listening. Any remaining questions? Okay. Yeah, sorry.
Maybe just one small question or discussion. Have you tried, maybe you have some data on the scalability? You know, how many sensors or how many processes have you tried to combine at maximum and throughout performance of your system? I mean, just to give a feeling to us. Like hundreds, or it's
Just not in real world experiments.
So you did simulations, right? Or
We did simulations to some extent, and we did realizations, but always with just a few sensors, like 5, for instance.
And simulations using which tools? I mentioned you've done it not on the level of the network, but on the level of the services. So you just use the materials like MATLAB, or you use
No.
specific simulation?
We used a specific sensor network simulator, which is called Sean.
Okay.
So Sean is able to simulate lots of sensors and pays for that by abstracting away from the physical details.
Okay. So it's not about simulation of networking protocols, but more on the services.
More on the higher levels.
Okay. That's the application level.
Yeah, that's right. Yeah. The nice thing about Sean is that you can use the same code for simulating and for execution on the sensor node. So we have hardware abstraction layers for different platforms, which allows really using completely the same image in the simulator and in the then later on in the platform, which is very important for producing realistic results.
Yeah. Okay, thank you.
Okay.